Okay. So welcome to the first ROS Live show of the 2008. I'm very glad that we have started again to start doing these ROS Mastering Live shows and helping you on solving your doubt in real ROS problems. So let's make this 2018 a big year in terms of ROS learning. And we are starting here today to learn about this, about how to make a good learning in ROS. So let's start with the question of today, the main problem, let's say. And it's a problem that has been asked many, I would say even months, maybe a couple of months ago. And then this question, it's related to having a laser that is rotating on top of a vehicle. So that's, for example, that's an example of the autonomous cars, that they do have a rotating laser on top, and that's a leader. And then they have to use this, the rotation, in order to detect the obstacles for all the sides. And then the question was about how can we use this in ROS? How can we make the detection of this laser to be on the same frame as the robot, and then move at the same time as the robot, as the vehicle is moving? Because the problem is that you have the rotating laser there, and then the vehicle moves. How you can accommodate this in order that the detections are moving at the same time as the vehicle, the detections of the laser. So we are going to see an example about how to do this, and let's see how it works. And then let's see, for that, we are going to get back to the example that we got in our first live show. If you remember on that, you can watch it online in case that you didn't. There, we created a rotating laser there. And then we are going to use this. So let me share the screen with you so you can see what I have prepared in order to show you how to do this problem, how to solve this problem. Okay, so here you can see the ROS Development Studio. We are going to use it in order to solve this problem. And for that, I have here a calculating workspace, and in the source, I have the simulation. Well, it's not the simulation, but it's the description of the rotating laser example that we had on the live show number 1. You can go back and then watch it. Then what I'm going to do is I'm going to launch an empty simulation and then instantiate this rotating laser robot, let's call it, and see how it works, just to remind you, okay? So in that case, I'm going to select an empty wall. Just clicking there, it will start the simulation with an empty wall. So now here it's producing all the messages related to the simulation as it is starting. And then in a few seconds, we'll have here our empty simulation. Here it is. Okay, so far so good. Empty. Then what we are going to do is, let me just clear this. And then let me launch this rotating laser description. Okay, we have here a launch file that allows us to launch the rotating laser and create rotating laser description, and it's called star rotating laser launch. So I'm going to launch it, and then we are going to watch it here. So it's loading. It has appeared here on the corner, and it is rotating. Here it is. So that is the laser that we are going to put on top of one of the cars that we have. So how can we, if we are receiving the data from this laser that is creating a point cloud of these rotations, then how can we get this into our autonomous car? So for that, what we are going to do is to launch the autonomous car simulation. If you come here, you can see that we have many other robots that you can just launch the simulation by pressing here. Let me show you the autonomous car one. So I'm going to press here. So we are going to receive now to get instantiated, launched the simulation of the autonomous car. Then this is the simulation that we are going to use, this autonomous car. And what we are going to do is to put this rotating laser that we have created here, that we have in this rotating laser description, and we are going to put it on top of the car. So here we have the autonomous car simulation. Here it is. At present, this simulation has a Hokuyo laser here that is just there. It's just a Hokuyo laser that is just sitting there in order to detect obstacles to the front. Okay, but what we have to do is to modify the URDF of this simulation in order to change this Hokuyo by the rotating laser that I have shown you before. Okay, then in the way that the ROS Development Studio has been created, at present, this simulation, as it is here, cannot be modified because it's just a launched simulation. So this simulation is provided to you in order that you can use it as it is. So in the case that you want to modify this simulation, we have to download it from our Git repository. So any of the simulations that you can access here, any of them, if you launch it, they will appear here as the car has appeared, but you don't have the source code. So, oh, okay, I want to modify the source code of this simulation. If that is the case, we have to go to our public simulations repository of the construct. So I'm going to provide this address for you and in the notes of the program. So afterwards, you can go and watch it and download all the simulations and models that we have in the ROS Development Studio. All those simulations here and more that we are preparing and about to come. Okay, so in this case, we are going to use the autonomous vehicle one. So I'm going to select this one and I'm going to copy this code here in order to clone it. So I'm copying this and then I come back to the ROS Development Studio. I'm going to do a clone of that Git into the ROS Development Studio for that. So we have different workspaces in ROS Development Studio. The one that we have been using with the rotating laser is the Catkin workspace because this is not a simulation per se. It's just a description of a robot and other programs, other ROS programs related to that robot. Then if we have to create a simulation, a specific simulation for testing all the code in the Catkin workspace, then we have to go to the simulation workspace. So I'm going to select the simulation workspace here. I have another Catkin workspace, different one, and then inside the source there is nothing, just an RBase file that I have created previously. So we are going to do the git clone here in that source directory. For that, I'm going to use the shell here. Then in this case is, let me see. Okay, so it's the simulation workspace inside source, and then I'm going to do a clone of the git that I have selected here, okay, of this git there. So let's go. In the meantime, I see that there is a question in the chat that is by Sagar Saha. Can I have the same studio? Yes, of course. You can access the ROS Development Studio at that address, rds.theconstructsim.com. I will also put the note in the notes of the video. I will put the address for this. Okay, so you can access, you can create a free account and then do the same thing as I am doing here. Okay, so I have cloned this git, and now if I do a refresh, rescan, then I have here the autonomous vehicle. Okay, so here it is with all the packages and code. Great. So now what do we have to do? Then in this case, what we have to do is to modify the URDF that describes this vehicle. That I know where is it because I have done it before. And then it is included here, and URDF in this package that is called Catkin Vehicle Basics, Cat Vehicle, sorry. And then the URDF, and then we have to use the Cat Vehicle mod. Okay, so here we have the URDF. Now, what we have to do is to change some part, the one that is related to the Velodyne here. Let me look for Velodyne. And Velodyne. I don't know if we are going to have a lot of Velodynes. Yes, we do have a lot. So maybe I will reach faster if we go here, because I know more or less the URDF of this. Yes, here it is, Velodyne LiDAR. So this is the code that is describing the links and the joints of this sensor here, or of this Hokuyo laser that we have there. So what we have to do is to change. It is, sorry, let me see, camera joint is not that, is here. Okay, here, it starts here. So this is the joint that connects this part with the laser. You see here is the Hokuyo laser inside this link, the Velodyne link. So what we are going to do is to replace this by the code of the previous rotation. Then I have to go to the, to the Catkin workspace now and check the code of the rotating laser description that is the URDF that is described here. So I'm going to open it, and let me put it bigger, and also to signal that this is an XML because it's not detected by the extension. So now we have here the description of this robot rotating laser, and basically it consists of two links. So, and one joint that connects both of them. That is a rotating joint. So I'm going to copy this, and then put it here instead of the link of the Velodyne link and the joint of the Velodyne link. Let me see. Yeah, so here, let me just connect this and then see, remove this. Up to here, and I'm going to put it here. The link of the base of the laser, of the rotating laser, and then the laser link, that is the laser that is rotating. So now, what I have to do is you have to change the name. I'm going to change the name this in order to make it more clear. I'm going to call it rotation laser base link. Okay. So then the parent link should connect to this other link, the rotation laser. So I'm going to change this Velodyne link by the rotational laser base link. And then we have this joint connected to the rotational base link laser base. And now let me also change this here in order to make it more clear to the rotational laser link. This is the link that contains the actual laser that is going to rotate. Then those two links are united by a joint that is of type continuous. And then I have also here to specify the change in the names. This change in the names, I'm doing this just in order to make it more clear, because starting to have lasers all around, so I want to specify that this is the rotational laser. And here we have, I think that we have everything from that point now. So we have the links and the join. Now, the next thing that we have to specify here is the transmission that specifies how the controller is going to work in order to make this rotational link. And this is included here in here in the, this is the code of the rotating laser description, okay? This is the one. And I'm going to copy just the transmission here and put it here on the vehicle URDF. So I am specifying, hey, we have a transmission with this name, and then the joint name that is going to use to control this transmission is the base to laser joint. That this one is the joint that we have specified here. Okay, so far so good. Then finally, we have to indicate the controller, the plugin for the laser. And the one that is included here already also in the URDF of the rotating laser description. So let's copy this also. And here, let's put it, for example, here. Okay, so now, I don't know, let me see if I have to change something. In this case, gazebo reference, yes, rotational, laser link, and then here also, let's call it rotational and rotational. Yes, okay, so if I have done correctly, let me check it. Yes, I think it's okay. So far so good. So by doing this, we have specified now in the URDF that this laser here has to be changed by the rotational laser that I have shown you before that was rotating. Okay, so I'm going to save, and we have that already. Now, what we have to do is to also indicate the controller that is going to control this joint. So it has to be loaded when all the other controllers of the simulation are loaded at the same time. So how do we do that? Okay, so this is specified in this config file. For the rotational laser description, I'm going to copy this. Open. I'm going to open. Okay, so I have it here. This is the controller that needs to be loaded for the rotational laser. And what it specifies is that it has to load the joint state controller, the general, in order to publish the state of the joint, and then the controller that will actually control the position of the rotation laser is this one. So this is the code that we have to indicate to the new vehicle URDF, that it has to be loaded. This is the controller that we have to specify. How do we do that? Okay, so we go to the CAD vehicle simulation that is here. We go there. And then we open the config file that contains the configuration of the controllers of this robot. And it's this one here. And then we just add this controller here. And by doing this, what we are indicating is, hey, when you load this simulation, please load also this controller. And what does it does, this controller? Is the one that controls the rotational joint. And how do we know? Because we have indicated here, base to laser joint. That is the one that we have included here. Let me show you base to laser joint here in the transmission tag of the simulation. So here we are saying this joint name is going to be controlled by this controller. Okay, great. Then, now, what happens? Once we have included this into the YAM file of the vehicle, we also have to specify into the launch file that launches this simulation that it has to load this controller, because this is a list of possible ones that are available for the simulation. But we have to specify when we load the joint state publisher, when we load this in the launch file, we have to specify which controller we have to use from the ones of the YAM file. So we are going to do this. And then this is included into the CAD vehicle control launch file here. here, let me put it a little bit bigger. You see, when we load this, is when the simulation is being launched. Okay, you can check everything, the whole thing, but it's not necessary now in order to talk about the rotating laser. But if you follow all the launch files, you will see that finally you reach this launch file where the controller spawner is being loaded. And in this case, we have to specify which controllers we want to use from the YAM file here. And of course, all of them already are specified, and here, that are specified here, but the newly added by us is not. So we need to say, hey, please also load this one. So I'm going to copy this name. I'm going to add here somewhere. It could be here, just as an argument for the controller manager. Okay, so by now we have the whole simulation configured. In order to accommodate here the rotating laser and to make it rotate. So what does it remains? What it remains is that we relaunch the simulation and relaunch the simulation, but in this case, it will take all these new parameters. For that, we have to press this button here. It's the relaunch, the running simulation, and here we have many launch files that are included in all the packages here. And the one that we have to launch is this one, Autonomous Vehicle Simple Main Launch. You can experiment with the other launches and see the different configuration, etc. Now we are concentrating only on this problem that we have about the rotating laser. So far so good. So we have done is first, we have in the meantime that the simulation is being compiled. Now it's being launched everything. So in the meantime, let me summarize. What we have done is, first, we have created, in the simulation workspace, we have cloned our autonomous vehicle simulation. Then we have modified the code of the car based on the content of the rotating laser description. And then we have relaunched it. That's what we have done. So now, if everything is okay, we should see here the rotating laser there. Okay, there it is. You see, instead of the Hokuyo that was sitting here, we have the base and then the rotating laser. I don't know why it's trembling now. Really don't know. So maybe something I'm missing, or I don't know. But the thing is that the system is correct. Now, why is not rotating? Well, because we are not launching the rotating program yet. In order to make it rotate, we have to launch this rotate laser program that we provide. Then let's do it. So I'm going to launch it here in the shell. And for that, it's as simple as ROS run. Is rotate laser is the name of the package, and the StarPy is the program. Rotate laser and StarPy. So now it should start rotating. Okay, so it's rotating something weird. It's kind of trembling. Okay, but so far so good. It's rotating. So I don't know what is this trembling. Really should go deep into the code and see what. Maybe I have put something wrong. I don't know. But as you've seen, you have seen that this was rotating perfectly when it was standalone. So I don't know. We'll check later. But from now on, it's okay. It's rotating more or less. Then let's go and then launch RBIS and see what we are capturing here, okay? So in order to do that, let me just change this visualization so we can have a better view of the simulation. And then let's launch an RBIS. For that, I'm going to open a new shell and launch here the RBIS. And for the RBIS, I have created my specific configuration that is already prepared for this experiment. So so I have launched it properly, but in order to see the RBIS window, I have to come here to see the graphic tools here. So I click there, then I open, and then I see here what graphic tools I have launched in my shells. In this case, it's RBIS. And so far, so good. We have here the car, then the rotating laser with this trembling, and then the laser that is that is detecting the scan. Okay, so far so good. There it is. Great, and it's detecting here some of the obstacles that are in the simulation. Great. This is not enough, because what we want to see is the point cloud. We wanted to see the point cloud, and for that we are going to use a previous work that we did when we were working on the rotating laser, that is how to convert the rotating laser, a laser that rotates into a point cloud. And that's a program that was explained on the ROS Live Show #1, laser to PC. So I'm going to launch that one and convert and start generating point clouds from the laser. So I'm opening a new shell here, and I'm going to launch the laser to PC. It's what's called like that. Let me see. Yes, laser to PC. Then the launch file is a star converter. Okay. Then, well, tap, and then there it is. So now we have a program that is generating the point cloud. And then here that is, and here we have the laser. So I'm going to disconnect the laser from being shown in the RBase. I'm going to connect the point cloud now. Let me just tell you that I'm seeing a lot of questions on the chat. I cannot answer right now, but once I finish this, I'm about to finish very soon, so I'm going to answer all the questions, okay? So just bear with me. Then what we have there is the point cloud, of course. So here it is, the point cloud, with the detection of the car and the free space and some obstacles that are here on the simulation, as you can see. Those obstacles are there. And yeah, what happens here? Why is so strange, this information here? Oh, yes, it's because the simulation of the car, the collision part of the simulation does not follow the shape of the car, but instead is following just a box. So it's like the car, for collision purposes, was a box of this size. So let's do one thing before we finish this. Let's modify this URDF. So we indicate that the car is not a box. So you cannot treat it like a box for collision purposes, but as a car. And then we'll see a better way of the lasers. So for that, we have to go to the CAD vehicle chakra URDF, basically. And then we have to look for the die of the car. Let me see. Here it is. Udemy car. Yes, that's it. The car body. And basically, what happens here is that the collisions of the car, you see, the geometry of the collision is specified as a box, but the visual is specified as a mesh file. Of course, the mesh file is the one that shows the beautiful car. That's the mesh. So let's do one thing, and let's change the whole collision by the same values as the visual. Why I'm doing this is just for visualization purposes. And why was set as a box prior to this? Well, it was set as a box because it simplifies the computation, and then it makes the computer to go faster. So it's a trick that you can use in order to make the system go faster if you want. Okay, so yeah, I think I messed it up because, let me see. Yeah, so I didn't close properly one of the tags. Now here it is. Great, we got it. I save it, and then I'm going to relaunch that. So in order to relaunch, I had to close everything. Of course, well, some of the processes will close automatically. So I'm going to relaunch here. Then I go to the autonomous vehicle sample main launch, and I'm going to relaunch. Then we have, this is the start to PC is being killed automatically. And let's also close the RBase. And once this is finished loading. You will see that visually is exactly the same, but the only thing is that the collision of the laser is different. You will see the pattern. And here it is appearing. Great. There it is. Let's launch the rotational program here. Then it starts rotating. Then let's launch the laser to point cloud converter. And then let's launch the ROS again. Here it is. We switch off the laser and switch on the point cloud. Okay, that's different. Okay, so now we can start seeing that the collision is different. Is moving the collision on the shape of the car, you see. Okay, great. Okay, so far so good. And it's detecting the obstacles that are around there. Okay, so now final thing. Let me just move the car so we can see how this point cloud is being transformed by the movement of the robot. So the point cloud is following the robot, the autonomous car. That was basically the thing that was asked for this ROS live show. And how did we achieve that? By integrating into the body, into the URDF of the car, the rotating laser, as you have seen, in the joints. So we have included into the joints. Another way would have been not to integrate into the URDF, but to include into the simulation as a different robot and then provide a static transform. That's also possible. It's a lot, it looks simpler, but it's more complex at the end because you have different robots and you have to specify namespaces and etc. But that's one solution, okay? So now we have the robot there, and let's move the robot a little bit. So for that, I'm going to open a new console, and I'm going to launch a program for launching the keyboard control of the robot. So I'm going to ROS launch. It's called CAD vehicle test. Remember that you have all this code of the autonomous car. It's available on the Git that I have cloned. So I'm not developing anything here. So I have launched it here, the CAD vehicle controller with the keywords, and these are the keywords that I can press. So I'm going to detach this screen, and probably you will stop seeing this screen because I have detached from the main application that I am sharing with you. But don't worry, what I want you to see is how the car moves. So I'm going to press the keys now, and the car should move. Okay, it's moving. Then I'm going to make it rotate. Okay, slowly. So we can have, so the car is rotating, okay, in this direction. Now, if we go to the ROS, we can see how the obstacles are changing the position in order to accommodate to the new position related to the center of the robot, of course. You can see that this is a visualization of a point cloud, so it's slow. Okay, so you have to be patient with that when you are managing point clouds because it's slow. But as you can see, the robot is moving around, and then the locations of the different shapes are changing. And if we go back to the robot, so the robot is here, all the obstacles are on its side, and that's what is happening on this side. They are appearing here. They are being cleared every time that the point cloud is generating a new complete round. They are cleared. Okay, so this is basically what the person was asking about. How can you create this point cloud, and then this point cloud moves with the obstacle. So that's all for this problem. Then another thing that, what are we going to do now? So I think that we have some questions. Let me check first those questions on the chat. I'm going to close the the movement of the robot. And then let me see, many things. Okay, let's start from the beginning. So yes, Saha, it says that can I have the same studio? Yes, you can. As I explained, you can visit the ROS Development Studio and just start using it. If I want to implement the same Saga says, if I want to implement the which microchip, should I use? Okay, I don't understand that question. Please rephrase. Muhammad says, can you please share the link for our studio? Yes, the link for our studio, I'm going to share it here, but it will be also included into the notes of this video. When we finish, this video is going to be available for anybody. So you can watch it later also, in case that you miss some details. So this is the link for the ROS Development Studio. Okay, so next question by Harryman. All coding is currently done in Python. When do you plan to have tutorials and the course in C++? Yes, good question. So this week on Friday, we are going to publish our first course in C++ of ROS. It's going to be ROS Basics, and it contains just the basics of ROS and shows what is a topic, what is a service, how to create messages, compile everything, and then you are going to learn that using C++. So this Friday in our academy, it's going to be published in our academy. That our academy is called Robot Ignite Academy, and you can access there. robotigniteacademy.com. Okay, then Mohammed says, sorry to ask this question early, but for some reason I have to leave now, but we'll watch a video later. Yes. Can we simulate a magnetic gripper in ROS Gazebo? I will listen to your answer later. Okay, so you can simulate everything, but not off the shelf that I'm aware. Okay, so I don't know if you can simulate off the shelf a magnetic gripper. You can create plugins for doing a magnetic gripper or whatever the sensor that you want to do in or actuator in Gazebo. So you have the potential for creating that by yourself. I don't think that there is a magnetic gripper somewhere. I don't know, sorry. Robert Vantit says, I have a toy car. There is a servo motor on his wheel. How can I communicate the leader with the car when I put the leader on it? Wow. Okay, that question is too broad, is too big in order to answer here. You cannot communicate the leader. So with the car, so I don't know if it has to have a computer or a car, an electronic car that acts as a computer. For example, a Raspberry Pi or an Arduino, something like that, that you connect the leader to that board or to that computer. Then by doing this, you will have some software that connects to the leader and then receive the data from the leader. That's all. If you do that in ROS and your leader is one of the popular ones, then you are done. It's very easy. You just have to connect and usually through USB, and then launch the ROS node that communicates with the leader. Stravos is asking, is there a specific leader that is used? No, in this case, it's just a simulated Hokuyo that we have increased the range. In this, Hokuyos only have 4 meters. That's a specific model here. So that specific model, it only has 4 meters. But we have increased in order to make the simulation here. Then you can use any leader that is available. What I would recommend you is that you check that this leader is ROS compatible. Okay, so in order to check if it's ROS compatible, you can go to a shop that is online that is called ROS Components. ROS Components, let me show you here, ROS Components. And there you can find a lot of components that are directly supported by ROS. So you can find anything that you buy here has a driver of ROS. So I really recommend you that you visit this store, this online store. Great, more questions. Steve Duncan says, Mr. Tellez, I have a question. How can we do this on a real toy car, not a simulator? So how do we add moving TF to the car, to the URDF model? Thank you. Okay, so in a real one, you need to have your joint state publisher and the robot state publisher. So those are the ones that publish the TF. Well, actually, it's the robot state publisher, the one that publishes the TF based on the values that the joint state publisher is publishing. So, Steve, for you, you have to learn how the ROS state publisher works and the robot state publisher works and the joint state publisher works. So you can check some of our courses that are online that explain this. Like, for example, it's called the URDF ROS tutorial. Let me show you. It's here. So in this course that we have, URDF tutorial. Yeah, well, here it is. So you can check this tutorial, robot creation with URDF, then we explain something there about the URDF, and also there is another one about TF. So you have to study those two courses. Then let me show you. URDF, ROS, TF, control. And it's called Ignite Academy. And here, yeah, here it is. Okay. So here you have all the courses that we have, and then I would recommend you to do this TF ROS course. Then you have to do the, let me check, the URDF, and maybe also the ROS control. I'm not sure, but those are basics. URDF1 and TF, you have to do those, and then you will understand how to use the robot state publisher and the joint state publisher. Okay, so Strabo says checkout. Okay, no questions. Your car has a Linux. Okay, something, yes. Okay, so what is the difference between, Muhammad is asking, what is the difference between ROS Development Studio and Ignite Academy? I'm ROS ambassador and arrange my next meetup at ROS Development Studio. Okay, so the ROS Development Studio is a place for development. So here you have to develop all your code. But instead, on the Robot Ignite Academy, you have a specific, sorry for that, there are some books that fall down. So you have some specific courses that are already created for you and ready to be learned. So when you start a course in our academy, for example, this is ROS Basics, then you have here the lessons are going to appear. Yeah, so the different subjects that are explained to you. Also, you can watch in video if you don't like to read. But here is the specific code that you can execute here at the same time that you are learning, and then see the result on the simulation that is loading at present. So this is tailor-made. So it's a course that is teaching you how to learn a specific course of ROS. The ROS Development Studio instead is just a place for developing your ROS code without having to install ROS in your computer. And you can use a Linux machine, a Windows machine to develop with ROS, test with the simulations, etc. So here you have the different courses and different subjects for a specific course. In this case is topics, basics, and then we use the Turtlebot in this case. In other cases, we use the, for example, the BB-8 robot or else. Or drones in this case for ROS actions. It's a simulation of drones, etc. Okay, so we have 10 minutes left, then I would like to answer a couple of questions. Just a question that it was asked by Susan Gray some weeks ago, and then I will give you a coupon for a 10% discount in Robotic Night Academy, just in case that you would like to use it, to try Robotic Night Academy. And for that, the question from Susan is, how can I detect, how can I calculate the closest obstacle that is detected by a point cloud? And why is she asking this? Because we published a video some weeks ago answering this question, how to get the closest obstacle with a rotating laser. So this is, in this video, we explain how to calculate the closest obstacle with a rotating laser, but based on a laser scan. And then she is asking me, how can I do the same with a point cloud? Okay, the answer is very simple. It's very simple. Let me show you. So if I open a new shell here, now we have, in this simulation, we have a rotating laser, okay? And it's generating a point cloud. And this point cloud is publishing on a topic. Let's see what topic it is. ROS topic list. So we have a topic here, it's around here, it's called laser point cloud. Let's see what is the information of this topic, the type, laser point cloud. It says, your message is a sensor message of point cloud 2. Okay, so what is this message? How it is organized? Let's see how it is. So for that, we do a ROS message show, and we specify that sensor message, point cloud 2, cloud 2, and then it's going to give us the structure of that message. And we see that this message, every time that this topic, laser point cloud, is publishing one of those messages, what it's publishing is all this. You see this information. Here, there is a field that is called data. This data field is the one that contains the point cloud. So the data, actually, the point cloud. And the point cloud, what does it contain? Is distances to detected objects. So if I do a ROS topic, echo, only one, okay, of that laser point cloud, we'll see how much information is provided. You see, all this data is the data of the point cloud. And these are distances to different objects. Then what you can do is to, in the same way as we are doing in this video, that we go to the ranges and detect which one of the ranges is the closest obstacle, you can do exactly the same here for the point cloud. And go to all the data and check all of them, all the values, and check which one is the closest one. So this is in order to answer the question of Susan Gray about how to detect the closest obstacle by using a point cloud. Great. So the last thing that I would like to commend to you is that I would like to recommend you a tool for programming with ROS that it's called PlotJuggler. PlotJuggler is a tool. It's a very interesting tool. It's a free tool that you can use it and download it and use it with your ROS developments. That is created by Davide Faconti. It was my boss some time ago when I was working at PAL Robotics company. Now he's doing some other developments by himself, and he has developed this tool called PlotJuggler. Let me show you what it does. PlotJuggler is very useful for visualizing series. So imagine that you have created a ROS bag, a log with data from your robot, and then you want to visualize how that data changes with time. So you open the bag, and then you can use this graphical tool in order to drag and drop which values you want to plot, and also compare at the same time with other values provided by other topics. And at the same time, you can see how the values are evolving over time. So this is very useful in case that you need to check where your robot is failing, why it's failing. When I detect this sensor value, why the robot is not moving forward, why it's not rotating, etc. So you can check it at which point. And this is a very valuable tool because it allows us to visualize all the values that the robot is generating at time. So I highly recommend you. I will do a session one day with further details about how to use it for taking the more of this tool. So just give it a try and let me know what you think on the notes of the program. So we are about to finish now, but then I have here a last question from Herman that says, please answer the question about the documentation on C++. Okay, so let me see which one is that question. Harriman. Oh yeah, sorry, I missed it. Thank you for the C++ news. Do this include the books, and when will those be available? Okay, yes. So the question is for the course, it's going to be published now in this week, and then for the book, it will be published by the end of January. But it's going to be only the ROS basics, like the one that we have here. So this is the ROS basics, but it's one made in Python. So we are going to publish first the course at the Online Academy using the C++, and then by the end of the month, the C++ book of ROS basics will be published on Amazon. So that's it. That's it. Thank you very much. Oh, the coupon. So let me show you, let me give you a coupon that you can use at Robot Ignite Academy until Sunday, the 7th of January, and then you will get a 7% discount. In order to get this discount, you have to use it when you want to. So, sorry, it looks like there was some noise here. So you can use this discount coupon until the 7th, and then you will get a 10% at Robot Ignite Academy. So let me write it down here. We'll also written in the notes of the program, and then the coupon is Live Ignite 8. That's the coupon. So you can use that for getting some, you want, in case that you want to try the system for only a week, or maybe you like it so more and you want to get this discount. Take into account that this discount is going to be applied for the rest of your life until you unsubscribe. So that's a very big advantage if you can use it. Okay, thank you very much. Please stay tuned for the next live show that is going to be the next week. Send us your questions. You will see on the notes of the program, you will see a link where to send your questions of your real life problem. And we'll select one of them and answer it deeply, and the rest will be answered just more dynamically. And please subscribe to our channel so you will get notified every time that we publish a new video solving questions about ROS. We publish a video every day. So every day there is a new video answering questions. So thank you very much for your attention, and I hope that 2018 is going to be a super great year for all of us. Best of luck. Cheers, mates.